Doing it. Thank you. Hello, hello. Ahem. 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 Thank you. How are we doing, folks? All right. Glad to hear it. Glad to hear it. So the stream is not ideal right now, so I am recording locally. You should be able to follow along with the lecture just fine. So streaming folks, to be a little choppy, that is not my fault. That is FSU's fault, honestly. It works fine for my house. If my house has superior internet, that's someone else's problem. So anyway, so let's do a few housekeeping notes for the class as we're starting to come down the home stretch of the class, okay? So let's go a little bit of that. All right. So today, 2026-04-07. All right. Indeed. Okay. So a couple of things. So let's talk a little bit about the project. Okay. The project for the class. Okay. So we have two remaining key dates for the project for the class. Okay. One is April 17th, that's a Friday. I checked this time, okay, for those. All right, April 17th. April 17th, we want another project update from you. We're finishing grading up your previous project updates, okay? We'll have a Canvas assignment for this, just to make sure that you're on track for what will then be due on the very end of finals week, because there is no final for this class, as I've said many a time. May 1st. Okay, that's the very last day of finals week, 5 p.m. Okay, gives you plenty of as much time as possible. Okay, you're going to do a few things. You're going to do a final report on your project. You're going to do a video presentation. Ooh, don't relax. It's never been easier to do a video presentation. All you got to do, in fact, these days, if you want, you put together some PowerPoint slides. You're telling the story of your project and what you achieved and why. It's less than 5 minutes. Okay. If you're a huge group or something, you know, you can negotiate for longer. Okay. It's supposed to be a quick presentation. You can just go on Zoom, right? And you can do this record feature on Zoom to create an MP4 file of your presentation. It's never been easier than it is now. Okay, and you have to submit both of these things. And one thing, in addition, if you're in my other class, it's a little different. We do want a link to your code. Okay, so, and for a few important reasons. Okay, and this could be just a Google. If you have a Google Colab notebook, it could be just a shareable link to your Google Colab notebook that you use to run all this code. That's great. If you have a larger code base, just upload some kind of GitHub account, okay, something we have access to, something we can look at, right? Okay. But those are the key dates coming up for the project, okay? All right. So, and this report, we have a specific format for the report, okay? It's just an IEEE format. Really, it's just an opportunity for you to say, oh, here's an introduction. This is what our problem is. This is the model that we chose to try to solve our problem. Here are our results. That's what we're looking to do, okay? Video presentation, okay? Again, and this is something that it's supposed to be something that's like, you know, less than 5 minutes to tell the story of what you accomplished and what you did, all right? And everyone should participate in the group, should participate in the presentation. And obviously, everyone should be participating in the report and work that went into the report, okay? Now, a link to your code, that's important. Okay, because I do want to talk a little bit about the code, because as we're grading your assignments, okay, I am very happy that people have gotten through the assignments. I do want to let people know that I'm not saying anyone did this, okay, but hypothetically, if people went to a large language model to ask them to start their to solve their problem for them and just copied and pasted code from the large language model output, you know, we can tell. And look, I'm not here to be a scold about it, although I'm not a huge fan of using large language models to do all your work for you. They tend to hallucinate, bad things tend to happen. However, in these assignments, there are lots of examples out there that these large language models are trained on that are similar to them. So they're going to be especially good at these types of assignments. I mean, I intentionally don't give you the hardest assignment on earth that no one's ever seen before. because you're students, right? So you can all learn. And so, but sometimes there are a lot of look, me and a lot of my students, they will use large language models to help them code, and it's actually very helpful for helping to find errors. A lot of people have found. I've read some studies on that. That it's nice to help you kind of guide you towards solutions to problems, and that's fine. That's fine. But do not copy just the raw output from a large language model, put it in there, run it, and say that's mine, because it's not yours, right? So please don't do that. And we don't want to get into a situation where you turn in a piece of code and then we're like, say, okay, let's look at this code. And it's like, okay, how'd you do that? What does this mean? And if we talk to you about it and you like humana, that's not good. You know, and really, and I understand, and believe me, I can empathize that some of this coding stuff is new to a lot of people. I get it. I totally get it, right? We're here to help you, you know. I try not to act offended that despite me being so friendly and a television celebrity, that no one comes to my office hours, okay? I'm not that offended by that fact, okay? But if you're struggling, they're there for you. You know, we're here to help you, okay? All right? So just please take that into account because, like, again, like, and these tools, they can give you correct answers, although I'm convinced that they're not as reliable as people wish they were. But they're good tools, but you gotta learn the material, right? Especially in this day and age with machine learning becoming more and more of a footprint in our lives. I'm glad you're all taking this course. It's awesome, okay? But if you're struggling, or please come see us. Please come see us. We got Nick and Jacob have built these types of tools from scratch before, okay? And so we're happy to help you. Okay, that's all I'll say on that. So please make sure your work is your own work. All right. And again, I'm not saying any particular person did this, but but there are signs that we can kind of see, and we're like, okay, all right, okay. Any questions on any of that? Okay. We expect one more homework assignment for the end of class, for the end of the semester. Okay, we're figuring out exactly what's going to be in this as we're rapidly adapting our curricula for this what has been a lot of fun course. You have any idea how much fun I had on Thursday? Coding Silly Frog. I love coding Silly Frog. I drew Silly Frog in 2009 as part of like toward my thesis, and I was like, someday I'll code Silly Frog, and I got to do it all live with you, okay, for reinforcement learning. In fact, I had so much fun. I'm not even done with reinforcement learning yet. Let's talk more reinforcement learning today, because I feel like we want to connect some of the concepts that we've been covering, because a lot of the supervised learning stuff that you did for homework 1 and homework 2, we're using things like gradient descent for your learning, right? And so whereas we coded a Silly Frog on Thursday, there was no gradient descent. There was none of that. Where did my gradient descent go? I talked about how important gradient descent was. Well, let's bring it back today, okay, into reinforcement learning. That's our goal today, to get back to things like gradient descent and perhaps actually gradient descent by taking reinforcement learning to sort of the next step here. So let's continue with reinforcement learning. Okay. Okay. And again, this here, my friends, reinforcement learning and introduction. This is the textbook I'm talking about. I was thinking I should find a copy of the textbook, and I forgot to have one on my shelf. You know, okay. First edition I've got here. Okay. Second edition has more better stuff, but nostalgia. So from the Sutton and Bartow text. Okay. We're going to work toward what we call actor-critic methods. And for those of you on the stream, I apologize for the jitteriness. That's a FSU issue. I don't know what to do about that, but I can repost it at a higher frame rate based upon local recording. So thank you for your patience with me. Hopefully you can hear me though and follow along with the lecture. So actor-critic methods. So recall our value-based methods. Okay? where we had, and here's our example from last class, example, our silly frog. Okay, we had all these lily pads. And a mean gator. Right? And you got a silly frog in the middle. Okay. That could hop from left to right, right? The way we solved this problem is we assigned value to each of these lily pad states, right? And we would just update that value. Okay? Got that? Got that updated states. Actually, Nick. So. Anyway, so we had so we had a value function. V of S. You know, the idea is you have a state. Hey, I'm in that state. What's the value that comes out? And if you're in a particular state, let's say you're there, you would, in order to know what you want to do, is you look at all your actions that you could take and say, well, which one is going to result in the most value? Okay? Keeping in mind the value is reward kind of accumulated over time. Okay? The reward, you know, the reward was like, I believe was like -1 here, -1 here, right? And 0 everywhere else. You know, 0 everywhere else. We're living, we're cool, we're chill. In a gator, bad day. Bad day. With a gator, also a bad day, but that's just me taking shots at Gainesville. Okay. All right. My apologies to my Gainesville friends. So, all right. So, value function, right. But our policy is determined by assessing our possible actions and choosing the highest expected value. Right? So the policy, in a way, is implied by the value. Okay? There's this idea of what we'll call an explicit versus implicit policy. Okay? An explicit policy is something you say, this is where I am, this is what I do. And an explicit policy could be very simple. Okay? So I could be over here, and I'd say I could have a policy to get to the door. And my policy is literally, am I here? Take a step forward. Am I here? Take another step forward. Take a drink. Okay, another step forward, right? All right. Take a drink. All right? Meaning, I'm in a state, this is exactly what I do. You know, I can draw it from a probability distribution. It could be a little bit random. It could be like 90% of the time I take a step forward, 10% of the time I take a step to the side for fun. It can still be probabilistic, okay? But it's explicit. I don't have to do some kind of search or any kind of reasoning to figure out what the next best thing, what the best thing to do is. Whereas these value-based methods that I'm talking about, they require that if I'm here, I say, okay, I'm here. Well, what do I do? Well, let me look at all my possible actions. I could do that. That one's best, take that, right? I can look at all my actions. That. Oh, that's the best one, take that. So those in my optimal controls course, those are your optimization in the loop controllers, where every time step you say, okay, run an optimization problem. What's the best solution? Do that, right? called an implicit controller, right? Because we don't tell it explicitly what to do. Implicitly, we tell it by like what it values. It figures it out, okay? Now, what's the downside to that? Well, the downside to that is that this takes more, these value iteration methods, they'll take more effort to figure out what to do every single step, okay? Every time step, what do you got to do? Well, look over all your actions, see what you're going to do. Sometimes that's doable, but as your action space grows larger, the number of things you could possibly do gets bigger, that search gets bigger, right? And the number of different types of states you have to consider, the more onerous that calculation is going to be, okay? Okay? So that's what a value function method does. It says, hey, we know what we value. Based upon that, we'll figure out what to do in the moment, right? Okay? And to what degree is that even realistic? You know, just think about even how a person might be operating. You know, there's a lot of computations we're completely unaware of in our heads, of course, but like, it's a lot of mental effort to be like, okay, what am I doing? Why? What am I doing and why? What am I doing and why? What am I doing and why? What is even life? I don't know. Whereas it's like, okay, I just want to get to the door. Go that way, right? Much simpler, okay? So how do we get to something that's a bit more of an explicit policy? Well, I'll take you on a journey today, okay? And my hope is that it'll take us back closer to gradient descent methods. It'll take us back closer to these explicit policies and closer to deep learning. Because as much as I love Silly Frog, as is that person's phone, huge fan, right? It's not deep learning. Nothing deep about it. There's no deep neural networks. There's no neural networks, period, right? Okay? So let's try to see if we can get us toward gradient descent, stochastic gradient descent, to be clear. Things like atom. We coded atom in class. Was that neat? Yes, it was neat. Yes, we coded atom in class and showed how awesome it was. You know, this fancy version of stochastic gradient descent with momentum. Anyway, all the cool coding we're doing with no LLMs. I'll shut up. I'll shut up. Okay. All right. So today, we're going to try to do a couple things. We're going to talk about one. Updating the policy by examining the value function over all actions can be onerous. Also, even just updating the value function across the entire space and updating it across the entire space, that can be onerous. It's a lot of states. Okay? So can updating the value function across all states. That's what we did for Silly Frog. Silly Frog is a small problem. We can do it, update all the value functions. Shoot, one step, shoot, next step, shoot, next step. Value function across all states. That was a simple problem. We could do that. So ways of updating the value function. You can be exhaustive. That's doing everything. That's what we did. Brute force. We did brute force. We did everything. Every state we updated. That's what we did with Silly Frog. Okay? Or you could just randomly choose some states. Choose them at random. Okay? And anytime you're like, hey, just try things at random and see what happens, it's called a Monte Carlo method. Okay? Did anyone in a computer science like middle school and or early college class, like high school and or early college class have to compute pi using Monte Carlo methods? Okay, well, that's how you do it. All right, I'll stay right here. You draw a circle. Draw a circle and a square. Got to see that online. Close enough. There's a circle and there's a square, right? You randomly draw a point within that square. Random number 0 to 1, random number 0 to 1. Where'd it go? Randomly. Boom. Ow. Hurt the marker and therefore hurt me by extension. Okay? Was that in the circle? Yes, it was. Try another one. In the circle? No. Yes. Yes. No. Yes. I'm bad at random numbers, but I'm just counting up. Yes, no, tally, 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 tally. The ratio of how many are in the circle versus not in the circle, which you can compute just by saying, hey, is it within like, a radius of like, a squared plus b squared is less than or equal to 1. How you would check it. No pi required, right? You check it over and over and over and over and over again. The area of that box is, let's call that that's the diameter is just d squared. And the area of that circle is, of course, pi d squared over 4. So the ratio of how many end up in the square area total versus just in the circle area, that ratio, pi over 4, or compute pi. Okay. The more data points you draw, closer you get to pi. Anyway, we didn't do this in kindergarten or wherever they teach it these days. I don't know. Anyway, so that's a Monte Carlo method, right, of computing pi. This is a Monte Carlo method of For the most part, I've been Nick. You've been able to see the screen, right? Yep. Okay. Yeah, but you can see. But I had the tablet up, right, for that. A lot of that part. Anyway, whatever. Yeah, that's you're good. So, all right. So, Monte Carlo. So you can just randomly pick states and say, I want to update the value of that state, that state, that state, that state. Okay, and that's pretty good, right? Okay, but there's a more famous way called temporal difference, or TD learning. Okay? And the idea is that you just update the value of the states you visit. Okay? And here's the idea. So that if you want to update the state, the value function using TD learning, you look at whatever state you're in, V at your value at the state at the current time, okay? You're going to update the value at that state. You say, you know what? It's equal to the value you had previously plus some alpha times the quantity of RT plus 1 plus some gamma. Anyone remember what gamma is? It's like a coupon. Discount factor. Okay. Value function at the next time step minus, I'm going to scoot it over so I can make more space. Excuse me. Bad at hoarding space here. So let's see the V. Good. Minus V at S of t. Okay? What you're doing is you're comparing the value in the future, your future update of the value, okay? You said, okay, so here is Vs of t. See this right here, the value? This is the value that we expect our current state to have. I'm in this state right here, boom. Okay? and I estimate the value of this state is 10. 10 schmadiddles, whatever the unit is of value, okay? But then I take the action, okay, that I think is best for this state, you know. I take that action, all right, and I say, okay, well, what was the reward I got for that action? And what is the value of where I am at now based on that action multiplied by this discount factor, this number that's a little less than 1? You know, so that sort of that discounts the value of things that happen in the future, so it's not fully valued, okay? Or as you could say, this was, you could say, our prior estimate of value. Oh, sorry, that's the opposite. This is the new estimate, sorry. New estimate of value, I apologize. This here is the prior estimate of value. This was what we had stored in our value function. This is what actually happened, the value that we got. Hey, what we got minus what we thought we have, okay? You can consider this a kind of error. How wrong were we about the value of that state, okay? How wrong were we? And then we multiply by this, alpha. Anyone remember the step size from gradient descent? I'm sorry, that was a rhetorical question. I apologize. No, I'm very impressed that someone said 0.001. They remember the actual value I gave them, 16 weeks ago. Thank you, Angela. Now, does anyone, rhetorically, do people remember the fact that there's something as a step size in gradient descent? Yes, we do. Thank you. Good. Claw clap. Claw clap. All right. All right. That's your step size. That's how much you update your prior estimate of value. You know, if it's 1, you just completely ignore what your prior estimate of value is, and guess what? Now it's the new estimate. Okay? So this is it's temporal difference because it's looking at the change in how you assign value now versus you did before. You thought it was this good. It's actually this good. And maybe it was better. Maybe it was worse. Okay? And as a result, you only have to update the state that you're in with that value. You just take an action. You see, okay, well, we'll update the value based on that action. Okay? Does that make sense? So in a way, I mean, how you take that action, that is determined by your policy. So, and that policy could still be, oh, look at all my whole, suite of possible actions that I could have, and say, that one has the highest value, do that, right? You can still do that. But this is how temporal difference updates the value function, okay? Right? A famous example of how this was implemented for canonical reinforcement learning problems is backgammon, okay? The famous implementation for backgammon was called TD gammon. Okay. Now, back in even to this day, reinforcement learning people love to use games, like board games, computer games, as benchmarks for their reinforcement learning algorithms. And I get why. It's for a couple of reasons. It's one, it is an environment with a clear goal, a reward, and it's already coded in a computer already. It's already computer simulated. It's a computer game a lot of the time. So this temporal difference learning was particularly helpful in backgammon. It had limitations, for sure. I remember when I first started reading papers on the subject, and some people tried to do temporal difference Settlers of Catan, and it was terrible. In my opinion, it was terrible. Now, nowadays, machine learning algorithms are excellent at Catan. Like they're like grandmaster performance level, I think. And now it's just the game of like, what games can you get machine learning algorithms to just completely crush? Can I say this out? Yeah, I can say this out loud. A few years back, was contacted. I can leave out their name so that way it's anonymized. Not that they matter. Not that they mind, I should say. I was contacted by a deep learning researcher who had just done a big machine learning model for poker playing, and they said they were done with that project, and they wanted to talk about doing Survivor next. I'm like, how's that work? Anyway, it's like they thought that they could actually. Anyone heard of Diplomacy? The game of it's like a game of like global politics in World War II or something like that. Anyway, like some of these models were really good at diplomacy. But anyway, they were like, I want to do Survivor next. I'm like, you know, you have solar power on the island, or what are you gonna do here? Anyway, it was fascinating. It was really interesting. I hope that they ultimately try it. So that's TD update. Okay, temporal difference update. Okay, now that we have a way of updating this value function, which doesn't require like looking across a whole bunch of options. You say, here's a policy, do that policy, and then we'll update the value function accordingly, right? So let's look into the idea of separating the policy from the value function. Okay? Okay? Because it would be nice to have an explicit policy like we talked about. Like, I'm in this state, this is what I do. I don't have to reference the value function at all to ask it. This is just what I want to do. Okay? So the idea here is that you have your typical reinforcement learning environment where you have a policy, but this policy is stored independently. You know, it's pi. You know, he takes in a state and then gives you an action, right? That's what a policy is. And again, not that pi. I regret using that example. Okay. All right. And then that policy gives an action, which goes into an environment. An environment. And that action goes into the environment, and out comes a state. Right? And that's the core loop of what a policy does. It says, hey, what state am I in? Do an action. It goes into the environment. Here's my new state. Do my action, right? But here there's no learning. There's just some policy, which could just be literally just a list of states, and here's an action. It could be something more complicated. It could be a state that's a vector of, that's just a vector that goes into a neural network, and out pops an action, right? So as long as there's some mapping from state to action, it's a policy. Okay? And this policy does not necessarily need to reference, you have to ask a value function what's best at any given time in order to choose the action. All right? But here we have the value function. Right? The idea is that the value function here, it has to take in a state, has to know what the state is, right? And if it knows what the value is, okay, and that value can now be updated from the environment using something like temporal difference learning, right? Okay. And the idea is that instead of having a policy that is always asking the value function what's best, then I'll do what's best. The idea is that instead, the value function can just tell the policy when it's taken an action, it just tells it, was that better or worse than you thought it was, whether it was a good or a bad idea. Okay? We'll call the TD error. Okay? This is that error I talked about. Was that action that you took, did it do better or worse than you thought? Then the policy can just update and say, you know what, that was better than I thought. I'm going to up the probability I'm going to do that in the future when I'm in this state. Okay? And this type of method has a very specific name, because now this policy is just doing what it wants to do. It'll take feedback from the value function that says, hey, that was good, that was bad, right? But it's its own entity. It doesn't need to ask the value function, what are all the options? I'll weigh all the options and do that, right? little different, right? So the way we look at this is we call this policy, this thing that generates these actions, we call it the actor. And this value function that takes a look at, hey, this was the action that you took. I'm going to put a little action here. All right. Here's the action that you took. And here's the difference between where I thought that was going to be good versus how good it actually was. Like, that wasn't so good. That was better than I thought, or, those kinds of things. We call that, this value function, call it the critic. So this is the flow. So this is the flow chart for an actor-critic reinforcement learning method. This is an actor actor-critic reinforcement learning. Basically, you can just say, here's what I took. It's like, this is the action that I took in case it needs to have some value action pair. To me, the most important part is just the learning of the TD error, right? That TD error that we're talking about. We already covered it. Okay. It's this. This is the value we expected. This is the value that we got. What's the difference? It was better than we thought. Hey, do more of that, please. Do more of that. So you can have an update. Okay? The policy can update the probability it will take, a certain action in a certain state by assessing whether the action yielded higher value than predicted. Okay? So here we're going to call our little error, little delta, lowercase delta t. Again, it's this term we talked about where it's the reward we actually experienced plus the discount factor times the value of the state we ended up in, ts plus 1, minus the value we had in our function before that, in that time in the past. That's the temporal difference, the value we thought we would have, the value we thought we had before, the value we think we have now. So this is the TD error. And you can see that's that term that we had in the prior equation. Okay? And you can have a probability update, action probability update. Where the probability, you'll take that if you're in some state st, that you take some action at, you reassign that to be what your previous probability would have thought you would have been, 50% chance I do this thing, okay? If the error is positive, meaning it was better than we thought, then we add to it by some factor beta, okay, which is another step size parameter. I won't ask you, Angela, for the value this time, okay? I've learned my mistake, all right? That's another step size. How much of machine learning is just like, here's a step size. Step in that direction, it makes it better by that much, right? the thing about machine learning, there's, maybe you came in thinking it's all magic wizardry, and it kind of is in certain levels, but really just the math, you break it down, how much of it is that way makes it better. Move things in that way, right? That's what learning is. I mean, think about this even analogously, right? If I'm trying to learn how to lift up this this phone here, okay? If I am trying to, it's like if I put it in my hand, I was like, oh, it's heavier than I thought. Okay, well, I'll put more effort in, right? Oh, I learned, right? I did a little bit more of the thing that helped. Same thing here. There you go. That's an actor-critic method. Okay? There are many variations on this, okay? And we'll get to a particular type of variation as we start to motivate some of the challenges of when these problems have bigger and bigger state spaces, bigger and bigger action spaces. But that's temporal difference learning. That's an actor-critic method. You have a critic, which is really your value function, and you have an actor, okay? The actor does a thing, and then the critic says, that was better than I thought. Okay. Okay, then the policy is going to say, I'm going to do more of that. Worse than I thought, I'll do less of that. One could arguably call it reinforcement learning. Like a dog, training your dog. Question, Christian. So the question is, how do you initialize the action space so it does something, right? Because if it does nothing, it will never explore the space and will never update the value. Well, don't do that, Christian. No, but that's a great question. So just like in many other iterative searches and things like that, in optimal control, we talk about initial guesses. You have your initial guess for your neural network weights and biases, right? What's a good idea is you would initialize your policy to be maybe random actions that would move you around the space, okay? And then that gives it a chance to explore. But there are absolutely possibilities, Christian, where I tell it to stay there. It never explores anything other than staying there, so it just chills out, right? What in a more formal way, in reinforcement learning, is what people will do is they will randomize the environment, okay? So there are all kinds of tricks, okay? As we get it, let's see, we got about half an hour. There are all kinds of tricks. So if you have robots and things like that, in order to make sure that they don't get stuck doing the same thing over and over again, you will randomize the goal. You might randomize the environment, like if it's a walking robot. When we walked in our robot into the classroom here, we in the training environment, we will randomly push it around, force it to do stuff. We will randomly give it rough terrain, so it's not everything's flat sometimes. We will randomly tell it its leg is twice as heavy as it is. It's called domain randomization, right? And still, bad things can happen. These Christianian dilemmas can emerge. So, and a lot of time, and you're talking if you talk to people who are hardcore reinforcement learning methods, you're working in these applied control, they will have an idea of what they want to achieve already. And so as a first start, they'll do a couple things. Has anyone heard, I mentioned the video game StarCraft in one of these lectures here, okay? It's a very popular game, especially popular in Korea. It's basically a sport there. Now it's a sport everywhere, to be honest. It's a real-time strategy game, video game. And one of the earliest ways that they got a giant deep learning method to work is they didn't just use reinforcement learning out of the box. Here's your reward and go. They started by saying, here's a bunch of example games played by people. So the first thing I want you to do, machine learning algorithm, is not maximize your chance of winning. Just try to do what the person does. Do supervised learning. If a human does this, you do that. And it gets you kind of in the ballpark of the actions that you want to take. You bootstrap it, okay, is what it's called, all right? Then once you're okay, that plays kind of like a human, now use reinforcement learning, and it will do better. That's the idea. I left out one or two methods I also thought were fun, but those are the most fun, okay? Any other questions? Any follow-ups? That was a great question. All right. So we talked about actor-critic methods, right? And we are talking about these things that look a little bit like gradient descent. Oh, look, this is how far off I am. Now I add this little parameter less than or equal to 1, so less than 1, between 0 and 1, and I update it. Oh, look here, look at this thing up here. A step size, it's even an alpha. How cute. Like a gradient descent. All right. But now, my friends, let's get to where we actually really need to use stochastic gradient descent. We're talking about deep networks. Okay? So deep neural networks as policies. Okay? Now, then kind of the most like naive way to try to train a deep neural network as a policy might be just to say, hey, look, I have this thing called a reward. I can even add up that reward over time into something I call a value or something, an expected return over time. Why don't I just do gradient descent to make that value go up instead of down? Gradient ascent, if you will. Just change the sign. We follow that math? We can do that math in our head? Good, right? So the idea, so let's try to so how about trading a policy network by using gradient ascent. Oh, blow your mind right there, right? Gradient go up because reward is good when up, bad when down. Caveman, no reinforcement learning. Okay? Go up. On the expected return. Or reward over time. Not a terrible idea. How would that work? Well, recall that we have this policy. Call it pi of A. Sorry, call it pi of S. Make sure I didn't put pi of A up above. Excuse me. Pi of S. Good. Fantastic. Pi of S. In goes a state. Out goes an action, right? And this could be a deep network. This could be a a deep neural network, right? What's stopping you from doing that? Theoretically, nothing. Yeah, we can make a deep neural network, right? Question is, can we get it to train? Can we train it, right? There's our, there's our actions. The in would be our state. Just like we have any input or output to a neural network that we had before, right? And where does this go? This goes to an environment. And out of that environment also comes not only the next state, but also some reward, right? Some reward. And we could aggregate that reward over time into some kind of value, this thing we want over time. But what are we trying to do the gradient descent on, or the gradient ascent on? We want to update our policy parameters which are the weights and biases, right, of that network, of the policy network, right? Those are the parameters. Using their gradient effect on the expected reward. Or the value more generally. Okay? And this is a method, okay? This is called a policy gradient method. How clever. Okay? It's a policy gradient. Sounds simple enough. Why did I waste your time for the last like 4 lectures on other things? I'm glad you asked. Well, here's a twist, here's a challenge. We need to know the gradient effect on the reward, right? The reward. So we need to know the gradient of that, right? With respect to all of our policy parameters, the weights and biases. Here's the thing. While we are very good at getting the gradient of neural networks, and you are especially good because you all completed your homework too so well, right? What about this? Gradient of our environment? We don't always have that. What's the gradient of, I don't know, what are these, what's the gradient of StarCraft? I don't know. The environment is not something you typically have a gradient of. Okay? At least not an analytic gradient like we did with backpropagation for the neural network. Okay? We need to know not only the gradient, so when you change a parameter of that neural network, you know, some weights or bias in there, a little weight and bias in there. Okay? You need to know the effect of that on the reward. You could do maybe finite differencing, change that by a little bit, change that by a little bit, see what happens on the reward, but that's a lot of parameters, my friend, in a deep neural network to do that with. Okay? However, it can be challenging. To compute the gradient through the environment and reward function. Can be challenging. Not always impossible, but can be challenging. In fact, some of my graduate students are becoming increasingly experts at coming up with simulation environments that do give you the gradient. Those things exist, okay? There's something called differentiable. There's differentiable programming. Is that the technical term? Differentiable programming? Or what is it? You can have differentiable mathematical frameworks where you can write a line of code, and then when you write that line of code and you have a certain number of inputs for your dependent variables, for your gradient variables, that it will automatically, alongside, prepare to calculate the gradient of your entire code base. It's pretty cool. Okay, there's things called called JAX, is what my lab likes to work with. Okay, there's an automatic differentiation through a bunch of code, right? These things exist, but even then, even in theory, though, you know, computing the gradient through hard, non-differentiable events such as impacts. Impacts, you have a sudden change of state. Suddenly the velocity changes upon hitting the ground. That's non-differentiable in a number of senses. Okay? But the point is, it can be challenging to come up with a gradient through an environment. If that environment is a physics simulation of a robot, that can be a problem. And there are other issues with policy gradient as well. Policy gradient is it's very easy to get trapped in local gradient, in a local minima in the gradient. It happens, at least my students are trying policy gradient methods for robots. Like literally, they will come up with a environment that's written in JAX, a simulation environment that will give them the gradient, and yet the gradient descent can still really run into all kinds of problems. Okay, so, but that's not. There are other things we can use to help us. Okay. Such as our good old friend, the actor-critic methods. Okay? So, riddle me this, friends. Yes, this environment, let's assume we don't have the derivative of it. We don't have the gradient of what happens when you have a parameter in and what comes out of the environment. Let's just give up on that idea for now. It doesn't exist. The gradient doesn't exist. But when we send it in action, okay, we update here our value function. Now this value function though, okay, we could represent this value function instead of like a list of numbers. Couldn't that be a neural network? Sure, I ask forebodingly, and answer quickly. Yes, it can be a neural network, something that we can take the derivative of, as we are all experts in now. Okay? What if our value function was a neural network? Its only job was to take in the actions and the states and then fit value to it. A supervised learning problem, something we're all pros in. Okay? And then the policy, when it's acting, in order to get its gradient, all it needs to do is say, hey, policy, here's the action I took. Was that good or bad? If the policy is a neural network and the value function is a neural network, everything in there is differentiable. Everything. Using backpropagation. Okay? So iteratively, as you're learning, policy will try an action, it'll send it off to the environment. Then the value function will learn a differentiable representation, otherwise known as a neural network here, that the policy then can access and say, oh, okay, actually, looking at that value function, if I were to take this, if I were to bump up this action a little bit, according to the value function, the critic, that says that will be a bit better. So I will improve, I will do more of that action, please. Because the value function says that'll be better if the gradient goes up, line go up, if I change this action that way. And if I change this action that way, the line will also go up. Okay? So actor-critic methods however can represent both the policy and value functions as differentiable neural networks for convenient gradient-based optimization. So you could use full-on gradient descent if you want, but since we're dealing with sparse data points, we're probably using stochastic gradient descent, or specifically ATOM, these momentum-based stochastic gradient descent methods, right? So that means that the critic network okay, it has a loss function that's only job is to predict the value of a particular action in a state. So the loss function, or the cost function as we sometimes call it, the loss function is prediction error between predicted and actual value. Okay? That's the loss function, and gradient descent will try to minimize that loss and make that neural network for the critic as accurate as it can. Okay? For the actor network, that's the policy. The loss function is going to be -1 times, because we want to -1 times the expected return for actions in this state. Because we want big return. If we're minimizing it, we want big negative return. Okay? Just multiplying by -1. I trust your math skills on that. Okay? So now all of a sudden, we have a completely gradient descent accessible method here. Gradient descent methods rock. Okay? That's good. Now, I do want to take you through one last twist, because this in and of itself could work. Doesn't work as well as you might expect. Okay? In part because the neural network has lots of nooks and crannies in the decision space. It's just, there's lots of local minima that are bad. Lots of kind of bad things can happen. So in practice, you can get this to work for certain environments. And we'll try to get it to work ourselves, okay, in the very near future in code. All right? But there are additional tricks that people who specialize in reinforcement learning have found that are really valuable to coming up with a good policy or training a good policy, okay? Some of these things are things I talked with Christian about just now, all right? One of which is, how do you initialize your first guess of a policy, okay? So another of which is, do you just give it your ultimate goal to start with and say, try to do that? It might work. One thing people have found is that for walking robots, it's just saying, hey, you're a pile of parts on the floor. Yeah. This is your initial guess for your policy. Okay? And I want to get to the door and look cool doing it, right? It is difficult for these gradient descent-based actor-critic methods or these reinforcement learning policy methods in general to figure all that out on its own. It's such an open-ended problem. Trajectory optimization can do it awesome, by the way. Just a plug for my other class. All right. But what they instead will do is they will create what they call a curriculum. They won't tell it, here's the ultimate goal, do that. You train it like you might do like a baby. You know, I don't tell my baby, you know, go fetch the mail and expect it to work. You know. So instead, you know, you teach them to crawl. Then maybe stand up. Then maybe take a step. Maybe take 2 steps. You could shape the reward to do things that are closer and closer to what you ultimately want to do, like you're teaching it. Called a curriculum. Okay? Now, that's a bit of an art, right? Who designs the curriculum? You do. Based upon what you assume is an important set of steps to get from one task to the other, right? Okay? That's what some people do. But what often happens in the world of reinforcement learning is that these gradients will kind of take you off in weird directions that don't always work out well in the near term. So what they found is that it's not smart for just the gradient to just take you away, too far away from the policy that you already had. Okay? In fact, it's a good rule of thumb not to change your policy too much too fast. Just little steps, baby steps. Okay? Right? And it created this idea we call proximal policy optimization, or PPO. If you see a cool robot doing a cool trick, probably doing PPO. All right? Anyone know what proximal stands for? What's that? Close by, like proximity. It's proximal means close by. In fact, if you're talking about anatomy, okay, if you're looking at all the linkages on my body, sorry, I'm not a robot, but I'll pretend I am for the moment, right? The shoulder, we say, is proximal to my center. It's like a proximal joint, okay? And as you get further away, you get out to the end, this is called a distal joint. It's far away, distal, you know, you get it. So proximal means nearby. So the idea is that you are trying to optimize your policy, yes, but in a way that favors policies that are proximal to the current policy, right? So they don't go too crazy. So imagine here that you have, and basically what you're doing is the PPO engineers a loss function that, in addition to maximizing reward and fitting a critic network, penalizes policies that are far from the current policy. Okay? So PPO, you can just consider a loss, a component of the loss function, where your loss is now equal to the negative of your reward plus your critic fit error plus the distance from current policy. That's an equation that doesn't need a period. Okay, boom, right? Negative reward, makes sense. We want to minimize negative reward, which means we want a high reward. Fitting the critic network, that's actually something that is completely like that. It does not in any way conflict with trying to get a good reward. It'll just try to fit the network, okay? And distance from the current policy. So when I say distance, I mean if your policy before says I want to reach toward, I want to apply force that have me reach toward this pen right here, okay? And the policy I'm trying says reach far away, that's a big distance, right? It'll penalize that, okay? And there are mathematical ways to formulate that. But that's what PPO is. It's a loss function. And this, awesome. Okay? Let's see. Let's see if I can pull up a video here. Let's see. This is dangerous. Go wrong. Let's see. Unitary G1 dancing. Second here. Look at that. Look at this. This is all deep reinforcement learning. Now, we don't know technically what they do, but we've talked to people at conferences. They're using PPO, okay? There's a lot going on here. Not to mention that the reward function is in part literally trying to mimic a human behavior, okay? That. Go, gets up, that. So this is the actions that it's taking are a policy. It is measuring state. They love kicking the robots. We're not, there's a long tradition of kicking robots in my field, but I'm trying to get away from it a little bit myself. But it is one way to demonstrate. So anyway, a lot of that stuff, right? Okay. So that's and how does that work? Okay, they designed a reward function that was basically mimic a human motion. They gave it key points and key frames of a human motion, right? Okay. They had a critic network that would assess over time how much a set of actions would achieve value, and they would fit that, but they would also add a distance to current policy reward function. And there's more things on top of that. There's certainly some of that curriculum stuff I was talking about. Okay? Anyway, so I think that's about all we got for today for reinforcement learning. We'll see how far we get on Thursday, see if we can code up some of this stuff. Okay? But in any case, have a good day.